you guys. The I I started with the Deep Space Exploration Society, and that is a group out of Colorado Springs, Colorado, that acquired or was given a 60-foot or an 18-meter dish. You can see it in the background, my picture. They worked for about 10 years getting it together. And only in the last 2 years were we able to get some science out of it. And since we started up, we were able to pull 15 pulsars from it. And the main goal that I had was, one, document it. What I tell the group is, if you don't document it, it never really happened. It's just like trying to catch it, claiming you caught a big fish and you don't have any documentation of it, it doesn't count. And pulsars are like catching fish. You spend long hours or days trying to catch one, and you may get one out of a group. At least that's ours. Wolfgang probably has a different, he aims it and gets them. So he has better fly rod than I do for pulsars. But one of the main other keys is that once you do get pulsars or hydrogen or whatever the astronomical output or measurement you were trying to get, what do you do with the data? I mean, how is it useful? So I started a galactic navigation series. And so I started that with hydrogen, and I went to pulsars. And the reason I'm doing navigation is that my background is I'm a retired Navy submarine officer. That got shifted in the before I retired to building spacecraft for the Navy. Then I basically did in my civilian life did ground stations. My last job was the chief architect for the Air Force Satellite Control Network, which is all the DoD ground stations. So I became very familiar with big dishes and how they're tied together and how they communicate with satellites. When I retired, I discovered that I didn't know anything about astronomy and how am I going to use this big dish in receive-only mode to do anything. And since then, I've been teaching astronomy. I've been doing all sorts of things. So it's really opened up a whole segment of my experience here. So the goal here was that how do I use pulsars to navigate in space and just general space navigation? Feel free to comment anytime you want and or ask questions. I am looking at chat, so we'll do that. So how do you use pulsars to do galactic location in space? Pulsars are very much like a GPS in certain ways. You need more than one to determine your location in space. You need at least three to do three-dimensional geolocation in space. I did write this. This is based on a paper I wrote, finding at that website, Deep Space Exploration Society website, and with many other papers that the entire group has done over the years. So I'm going to go over some basics here. Basically, what's a pulsar? How do you do galactic path planning, pulsar visibility along the path? It might be interesting to note that as you go from one area of the galaxy to the other, you will not see all the pulsars you currently see, and you'll pick up more pulsars that you've never seen before. That's because they have such a narrow window in their pulse or in their as they turn, that we're only seeing a small fraction of the pulsars that are out there, just because don't happen to be in their beam right now. All right, but as you travel through the galaxy, you will see more of them as you travel through their beams of unknown pulsars. So just realize that we have not seen all the pulsars. There's a thing called a pulsar base period. In other words, what is the actual pulsar spinning at? this has a lot to do, this is sort of the time travel story of this whole thing, is that we are really looking at pulsars in their past, not their current, and pulsars are spinning down over time. So we are looking at multiple time periods in multiple pulsars, and I'll show you a tool to use that to figure out where you are. The ATNF is the Australian. Now I forget what it is. I'll get to it. The ATNF and SIMBAD databases have the current set of pulsars with their parameters in it. We also did a pulsar simulator here at the Space Exploration Society, which is very useful. It enables us to simulate a pulsar and check out all our equipment. I did put together a Excel three-dimensional coordinate computer using the solver program and Excel, and that allowed me to determine the three-dimensional coordinates based on pulsars and the measured pulsar base period. Then you have to select the pulsars. As I was saying, in order to do pulsars, you have to have more than 3, and they have to be visible along the path. So one of the goals is, how do I know that it's between like say the Earth and another planet, that the pulsars I selected on Earth are actually visible as I go to that planet? And you'll find that a lot of them aren't, because of they get out of the beam. Your path gets out of the beam of the pulsar. So you can't use all the pulsars you're using on Earth for navigation, for the complete path. Then, how do you solve galactic position? Okay, so that's the plan. I'm going to get it done. Paul, you're going to have to give me a 5-minute warning, because I easily can talk for 4 hours on this, and I don't want to, Pablo is a better talker than I am, so I'm going to let him. I want to hear his too. Okay, how do you do? What's the pulsar base? Picture is a pulsar is called a compact object. Compact object is started as a star, and for via supernova, via some star collapse, it's turned into what's called a compact object. It is basically held up. Gravity crunches it. It's being held up by the neutrons. It's a neutron energy. Just the ability of the neutrons to hold against gravity. So that's why it's a neutron star. If you get more gravity than the neutrons can handle, that's where it goes into a black hole. Okay, and at that point, nobody knows what can actually stop the collapse after a black hole. But it's just on the edge of having, a black hole fundamentally is the gravity is so strong that it actually bends light down toward it, and that's why you can't see it. It has a event horizon. Pulsars are on that edge. You can still see the pulsar. The electromagnetic energy still comes out of it, so you still have you still can see energy from a pulsar. Now, how does it work? There's basically a pulsar is spinning very fast, because when it collapses, it retains angular momentum, and that angular momentum from the diameter of a star down to a diameter of about 12 kilometers of an object causes a very fast spin rate, and an very strong electromagnetic field. That field turns into the beam we're talking about, and the only reason that we can see that pulsar is that we happen to be in the beam. Okay, if we were off the beam, we would never see the pulsar. That's one of the results of doing galactic navigation through space. Is if a spacecraft moves away from the Earth, it may not see the beam of a pulsar that happens to be aimed at Earth now. So that's one of you galactic navigators. You're going to have to go pick up more pulsars along the way and document them. This is a pulsar spin period. So the period is how fast is it spinning, and P dot is the first derivative, which is explaining how it's slowing down. It's slowing down because it is producing a lot of electromagnetic magnetic fields. Those fields are slowly spinning down the pulsars over time. So they go from, the spin period actually goes from a high rate and down to a low rate. This is a period, so 10 seconds is a long spin as opposed to 0.01 seconds. And so this is normally, crab pulsar somewhere over here. Some of the magnetars, that if you talk to Wolfgang, he's got them, found one over here. And so generally the life cycle of a pulsar goes from up in the upper left to the lower right, and they call this the graveyard pulsars, because at a certain point they spin down and they're not seen anymore. There's just not enough energy for us to see them. So a lot of the pulsars end up down there. Now, if they are a single pulsar without a binary on them, what'll happen is that they will stay in this graveyard here. But if they're a binary star with a pulsar on them and they come down here, what happens is some of these pulsars start eating their neighbor and start spinning back up. And they tend to drop down here and they turn into millisecond pulsars, very high speed pulsars that are in the milliseconds. So you got this pile here, or millisecond pulsars. These are also very hard. I have not detected one yet, but I think there's Wolfgang's got numerous of them, and but that's where they go, and that happens because the physics was that they started to eat their neighbor, and they got more, as they get more material, they spin up faster, and they basically come back alive from where they were. Okay, this is the ATN database, Australian Telescope National Facility. There, I got it. And highly recommend anybody interested in pulsars, go to this database. It's a fully searchable database. It gives you all the information about the pulsar. And one of the key things I was looking for here is, what is the galactic coordinates of the pulsar? The period, the P0 is the period, and P1 is the P dot, and it gives you the distance. So you have to have a relatively good knowledge of distance on this, at least for the first estimates. Okay. Now realize also, when you talk about galactic coordinates, there's two types that you'll see. First is the galactic coordinates you normally see, for example, in this database, are Earth-centered galactic coordinates. In other words, it's from the Earth to the position. So all the angles, the thing are from the Earth, etc. Then there's but in order to do galactic navigation, you really need to have galactic centric. So I want it from the center of the galaxy. So you have to make an adjustment to take Earth galactic coordinates to go to galactic centric coordinates. And there's a small, very easy way to do that. It's a small calibration on that. So realize that, and realize the period is the period observed from Earth, and it's not necessarily the base period. And I'm saying the base period is, if you're actually sitting on the pulsar, what is the period of the spin? And as opposed to, if you're on Earth, what is the period you're measuring? P1 is the spin down rate. That is also problematic a little bit. We're going to use that as a constant here, even though it's not necessarily. That is how fast it's, how it's slowing down. And slowing down can be affected by many things. There's things called glitches, where the actual spin shifts really dramatically, etc. So the spin down rate going to have to be monitored very closely in order to use this to gain accuracy on your navigation. Simbad also has a database. You can actually pull up the data on these this stuff too. Okay, now this is a little pulsar geometry here. You see the center of the pulsar is here. Here's the beam. What's the interest is this angle here of rho. That is the distance here that the between the center of the beam to the edge of the beam. The reason that's important is that the only way we can see the pulsar is if we're somewhere inside that beam. Okay, so if we were within 2 rho, the assumption is that I made assumption you can see the pulsar. It may be weaker on the edge of the beams from the center, etc. But the goal here was first cut, assume something. Now, one other thing is 90 degrees. If I had a beam of 90 degrees, there's a problem when the beam goes past 90 degrees, is that the closer it gets to directly away from being perpendicular to the, say, the north part of the pulsar, and if the beam comes down almost to 90 degrees, the edge of that beam is starting to get close to the speed of light, and there's a limitation on that. So it cannot be greater than 90 degrees because of that. And it's really going to be above 90 degrees normally. So, but anyway, so if I'm anywhere near the 90 degree part of that beam, I assume we could be seen by the pulsar. I need to make that assumption because when we do the math, I need to find the area, or I need to know how big the beam was so that I can determine if we can see it from the spacecraft. That can also be, the model will allow me to change that, lower the beam. That would just cause us to see fewer pulsars along the path. Okay, so I did a galactic path model. And this is relatively simple. Once you get the galactic centric coordinates, and you pick I picked a position from Earth to a known Earth, potentially Earth type exoplanet called Kepler 452b. And basically I did 3-dimensional galactic coordinates. And I said, okay, how am I going to get from Earth to here, galactic centric coordinates? And you need 3 planes. You need X, Y, X, Z, and Y, Z coordinates in order to do all 3 dimensions. Okay. So basically I split that up into 3 stops along the way. Why do I need to stop? Because I'm flying a faster than light spacecraft and I can't see a pulsar when I'm faster than light. Okay. So everybody, all you Trekkie fans, they really need something besides, your common pulsar detector if they're traveling faster than light. So I'm assuming I'm stopping at each of those locations to take a fix. Okay. Much like I had to do when on a submarine where I had to come up periscope depth, put my antenna up and try to find a nav sat somewhere. All right. Very similar to that. So I'm very in tune to what these guys have to do if they're traveling faster than light. They can't get fixes as they're going. Okay. Okay. The other thing to note is that there's a beam angle, but realize that there is a big loop, big area where you cannot see the beam on the inside and the outside. Okay. So there's just basically a donut of the beam here that you can see if you're on Earth. So your goal here is, if you're going to use a certain pulsar, you need to be staying in that beam along the path, right? So you either change your path or you pick up other pulsars that you can see in order to get, as many pulsars as you can to do this. Okay. So it shows the 3-axis or the 3-dimensional from pulsar for, the 14 here, here's 452b, here's Earth. So you can sort of see how that all sort of looks from a geometry point of view. Little math, I threw this just into, if anybody wants to take the slides and look how I got the math here. So the Earth pulsar destination angle here, you need to be able to find all these numbers, okay, in here in order to do the math right. Here's all the formulas to find those. Okay. I developed a tool using all that math in Excel, using the Pulsar database as my starting point to determine if the angle of the pulsar was along the path can be seen. Okay. So if it's greater than 2 rho, you can't see it. If it's less than 2 rho, you can see it. And so you pick your path, and then the tool will give me a green if I can see it and a red if I can't see it. All right, so now I can pick out my pulsars that are using the entire database. I can pull the pulsars that can be seen from Earth, because that's the only ones I know about right now, and determine if they can be seen anywhere along that path. And the goal is that along that path, say at the 25% mark, I might be able to find 6 pulsars there, but I'd have to probably find a different set of 6 pulsars or another along a different part of the path, because it would be out of the beam somewhere else. So is that our current database sufficient for that? That'd be the question. I'm sure the farther away we get from Earth, the more problematic it'd be that I can't use the Earth pulsar database without having more pulsars available. So that's why it's having missions going out, finding more pulsars farther from Earth is going to be important in our future. This is what it looks like. I left some of these open here, but the ones that are within the beam here are is that all 3 axes have to be visible. So for example, this one here is only visible in the XZ plane. It doesn't help. So they have to be only the ones that are visible in all 3 planes count, the ones I can use. Now, the model to figure out the angles, if you basically close all this stuff up, you'll see that everything in green here on the different axes is are the pulsars that are available. You notice that this is the pulsar database here with the J name here, galactic coordinates, everything. So basically this is all the model, and everything in green is good. Okay, this is what the pulsars look like that were selected on the galactic plane. I want to note real quickly here is that here's the Earth and here's Kepler 452b. They're extremely close together in galactic coordinates. I think it's 16 light years apart. And I chose that because that's a reasonable time to be able to get radio astronomy from, and if somebody was going to transmit. But look at where all the other pulsars are. Now, remember that the distance, the farther the pulsar is, the farther back in time we are seeing the period. So the way the model is going to work is that if I have the base period of a pulsar that's at 1 second, that if I'm 10 light years away, I'm going to see what that was spinning at 10 years ago. If I'm 20 light years away, I'm going to see what it was spinning at 20 years ago, and realize it's been spinning down all that time based on the P dot. So I'm using that property to determine, when I measure the pulsar at the spacecraft, what is that period, and therefore using the P dot and going backwards and knowing the distance from the database, what parameter, where am I in space in order to see that measurement? Okay, so I'm using that. So I'm actually using time, historical data, or not historical data, but a time machine to determine that. Now, if you do that with at least 3 pulsars, now you get a unique position that there's only a couple places without ambiguity that you can see that all 3 pulsars would be being measured from the distance they're at with their appropriate P dot, slowing them down over that time. There's only a couple places that could be in order to have a unique position in 3 dimensions. This is the formula for that, by the way. And what I did here is that, basically the base period, which is I'm calling, you're standing on the pulsar real time, said, what is this actually, what's the actual speed of that pulsar or spin rate of the pulsar? You got a pulsar as you observe, that's your measurement in the P dot times the distance in light years. Okay. So if you do that and you do 3, basically little trig here with distance measurements, you get a trial distance, pulsar distance here, and then you take that from the observed distance and you get a delta, and your goal is to get a delta of 0 on all 3, and that would give you your unique solution. 3 equations, 3 unknowns. Okay, and in order to do that, I use the Excel tool. This is what the model looks like in Excel. If anybody's really interested, I can send you the model and we can walk through it. But fundamentally is I put the 3 or the pulsars here that are, notice that they're green because that means they're all visible. And then I put the observed period. So this is the key is I stop 25%, I go into inertial drive instead of faster than light drive, and I measure the pulsar. So I'm fundamentally standing still, so I'm no Doppler effect. And then I measure the pulsar period. I know what the base period is, and then basically from that, I can calculate a delta using the solver in Excel. That would give me a X, Y, and Z coordinates in parsecs. That's what I've got here. So that is my position that based on trying to get my my delta errors down to 0. Okay. So and this would give me also a distance. What it'll do is it'll vary these. I'll vary these distances here and using all the math until the deltas go to 0, and that'll or as low as possible, and that gives me a position in space. Okay, with a certain error. Anyway, so it worked out pretty well. This is the solver configuration. I did find that there's a couple issues with solver that I'd rather have a more design something better than using solver. Obviously, once you get the basic concept, then I think you can do this easily in another program, and you won't have some of this thing doesn't like certain configurations that you put in here. So this configuration worked. I had some errors doing it different other ways, so I threw this out for anybody who wanted to try it. So you have to start where I did. It took me about 3 weeks to figure out how to get solver to work with this. Okay, what is my errors? Well, I calculated I got the standard error, and you can see based on, and what I did is I did it, what is the pulsar error based on 1 to 8 pulsars. And what you find here is that 1 pulsar gives me an error, but I don't know. I don't really have a good position. So I don't really know if I'm very far off because I only got 1 pulsar. If I do the 2 pulsars, I get really far, about 300 light years, so 3,000 light years away. Third pulsar comes right back down. And then after that, you basically normalize off until you hit about 6 pulsars. 6 pulsars is what I was using in this as the trial. More pulsars, better, but it'll give you an error rate. So big picture is at least 3 pulsars, and from this point of view is 5 to 6 pulsars is the best. That gives you a pretty consistent low error rate on your performance here. What does that error mean? Well, using 8 pulsars, I have an error here about 0.02 light years, and this is in kilometers. And you can see the edge of the Jupiter, Pluto, edge of the solar system. We're pretty far out there, but realize that Alpha Centauri, am I going to hit which solar system am I going to hit? I'm really close to our solar system here with my max error, and with 8 pulsars, and I totally miss Alpha Centauri, which is at a lot farther away, 4.3 light years, and I can get within 0.02 light years using this method. And when you get more, and once you get this method going, you get more accuracy, you get better measurements, pulsar spin rates, and better tools. You can definitely drop that number down to where you maybe get to the edge of the solar system or to a planet. So you don't use this method to aim at Earth. You're basically aiming at the sun, the solar system, and then you have to go use closer in navigation to refine your model in order to navigate through the solar system. But you can definitely get pretty close to the solar system with this method. Okay, so let's just do an example here. We're going to go to 452b, galactic coordinates, galactic centric coordinates. We have to choose the pulsars that are visible along the entire path. Observations, you got to stop to make an observation. You can't run faster than light speed and make an observation. You're going to calculate your new position and then make course corrections appropriately. So I am going to go, this is this before up front. You need to go 3-dimensional space, X, Y, X, Z, Y, Z planes. And we're going to stop every 25% of the path to take an observation and see where we're going. I selected based on the position at those points. So the ideal path is, assuming you're on course, you're 25%, 50, and 75% positions based on that at all 3 axes. All of these pulsars, you can see their names over here, are visible at those points. Now, if you look at the entire database, which I had set up for this, a lot of pulsars are not visible along the entire path, or are only visible at certain XYZ planes or whatever, but not through all 3 planes. So these are all 3 planes, they're visible, and you get a value. And therefore, these are all good for navigation. Okay, you run your model, and you find observed pulsar periods. Now, I cheated a little bit here. I actually assumed I was off course at the 25% point. So I put those numbers in. I calculate what those would have been at the off course position, and I put those here. And so it came up with a solution at this XYZ in parsecs. Now that's from the Galactic Center. And I came up with that at my 25% point, I was off course here. Okay, so what do you do now? I mean, as a good navigator, your joy is that you get a fix that you sort of trust, so you can actually do something to navigate. So here is the assumption here is that I'm off course. I'm going to have to change position 3-dimensionally. So I just can't aim here in XY coordinates. I have to aim there in XY, XZ, and YZ coordinates. to change to get back on course to the 50% mark. Now I can also go from that point right straight to 452b. The assumption here is that my original course, I was avoiding black holes and nebula and various things I didn't want to hit. So you'd have to do a lot more than just aim and go, because there may be a lot more stuff in between that, you know, a quick course correction might hit them. So the assumption is there's a lot more stuff there you got to do while you're navigating. So we calculate an updated course, figure out how long we need to take to hit the 50% mark, and then at the 50% mark, you do the same process, and you find another position, and you're good to go. Okay. So in summary, it's reasonable accuracy if you're going to aim at a solar system. After that, you need to go do internal solar system navigation, probably much like Voyager is doing now. You need a better thing than solver in Excel. I'm sure that easily will happen. Once you got the basics figured out here, basic math, you can do this in anything. The other thing is you can probably see in big pictures, you can probably see the Earth move. And I haven't done this yet. If you take, and this is something that, you know, maybe the guys who do pulsars, if you can collect a number of pulsar positions over time, over the year, another spin rates, we can actually do this and see if we can actually see Earth move in galactic coordinates using this method. So that would be the real term time observation, where you see if the Earth be used as a spacecraft and calculate its position over time. Now, in terms of SETI, I originally did another paper on using the pulsars on the Voyagers to, you know, for the ETs find it, they can figure out where the Earth is on pulsars. But I think if you can actually, this will be able to tell you which pulsars to use. You can't use any pulsars to figure out your position or an ET to figure out its position. You need to assume over time where that, let's say the Voyager is going to be in 1,000 years, and then say what pulsars are visible at that point to find out where the Earth is. And you're going to have to get more than 3 pulsars, because over time those 3 pulsars may not be visible. Okay. All right. Well, that was a fun exercise. And it can actually be used by students, and the math is relatively straightforward. But the goal here is that what can I do with the pulsar data once I collect it? Well, here you can actually probably track Earth around the galaxy using this method if you keep collecting the pulsars over time. Okay, Paul, any questions? Uh-oh.
Yeah, it's a good one. It's a good one. You saw that in the chat.
Oh, wait a minute, I missed it. Okay. How do you would you adjust for your expansion? Okay, so I'm calling this galactic navigation. Once you get past the galaxy, is pretty much not expanding inside the galaxy. The gravity is offsetting the expansion. It's really outside it's between galaxies that the expansion is happening. So that's why we're not having the big rip kind of thing or something like that. So I'm not accounting for expansion at all. I'm assuming we're just doing galactic navigation for now, and not intergalactic navigation. If you start doing intergalactic navigation, we do know the Hubble constant. We know approximately how fast everything's expanding. You'd have to add some more variables onto these equations to account for the Hubble constant expansion rates. And that'd be how I'd do it. I didn't do it in this. I assumed that we were not expanding inside the galaxy. good question though. That's a the golden record. I actually did a paper on this. One of my first papers to figure out. I didn't know anything about pulsars, so I actually figured out if I was an ET, could I figure out the pulsar locations on that? And if you go to that DSES website, you can find it. And it's a very interesting approach to the way they used dots and dashes basically to give an indication of period and angles, etc. And so yeah, it's on the Pioneer plat too. You're right. And so if you look at that, and I actually came up with what the error rate is. If an ET picked that up, could he find Earth? So let's see, I don't know how they determine which pulsars to use. I'm not sure that all those pulsars are visible. They used about 12 to 14 pulsars, as I remember right. And I don't know if all of those are visible. They're all visible from Earth. The question is, if Voyager goes out to Alpha Centauri eventually, or in that area, or at least that distance, is it, if the ET picks it up, then could they see all those pulsars? My guess is it's close enough. They probably could see most of them, but maybe not all of them. And all the three, and by the way, it have to be in all three dimensions too, all three planes. Okay.
Are there any more questions?
13. If we only slow down to sublight speed, would we be able to correct for the depth? Yes. The issue is that if you're faster than light, you can't see electromagnetic interference. So that beam, with the equipment we have now, of course, faster than light speed isn't one of those, but that's okay. If you're below that, you can correct for Doppler. If you know your exact course and speed, and it's lower than speed of light, wow, it gets hard when you start getting past like 0.3C or speed of light. My understanding that a lot of weird effects happen. So if you were dead in space, that'd be perfect. Then you can have a really great measurement. After that, you have to correct for it, and then that's just more advanced and relativistic advancements in measurements that you're gonna have to adjust for. It's teaching you how far can you travel in FTL before you're completely lost, or are you never lost? Oh, yes, you can be completely lost, but space is big, all right? So you can be knocked off course, and saying is, I think it was I forget exactly how many light years this was apart. It's going to be quite a while at the speed you're going at light years to get lost. All right, too far. You get lost within 10 light years or so. It's like a submarine, right? I could, as the navigator, it took me, I would not worry too much in open ocean if I didn't get a fix for multiple days, right? I just didn't worry because it's a big ocean, and I have a lot of area to fly in. If I'm traveling somewhere with close proximity to hazards like islands and black holes and other things, yes, I need a lot tighter navigation fixes and more of it. So it's not getting lost. It's how far, when am I going to start hitting navigation hazards and black holes? And I keep saying black holes, but it could be stars or, asteroid fields or whatever. On the periods caused by the pulsar's motion around the galaxy, their own proper motion. Yeah, that's not accounted for. And that would be something to add. That assumption here is that that we're all traveling in the pulsars are close enough that we're all traveling together, and as the galaxy spins. And I'm not accounting for the pulsar drift, but some of the new some of the new readings, I forget what's the new spacecraft that's given all those databases. That is also accounting for pulsar drift. And I did find that one of the pulsars used in the Voyager map was actually moved. It was one of those higher speed pulsars. It actually moved from the position it was back in 20 years ago or so. So they are moving relative to the Earth. They're not in the sky, celestial coordinates. They are moving based on how close they are. So yeah, we have to account for that. I did not hear. That's one of the adjustments to tune up your thing. Let's see. For pulsar pulse glitch, does the P dot rate permanently change? Is there a way to account for that? From what I've seen on the glitches, is that they form a definite change in the period, and they usually recover. Now, whether they recover to the exact period or P dot, I'm not an expert on that. But what I have seen is they do recover close to what the original was. And that's the other thing is once these guys glitch, my guess is you're just gonna have to monitor until you get a new decent P dot that you trust, that's been, years, that's steady state. And I would probably not use a pulsar that has a history of glitches because of that. Because if you're out in open space, you just don't know. If a pulsar, if it has a habit of glitching, you just don't know whether it glitched or not while you're in FTL, and we're out of the picture there. Okay.
Rich, thank you very much.
Okay.
Absolutely fascinating, captivating.
All right.
Next time we get you back, I'd like you to give a presentation on your faster than light propulsion system. That would be,
yeah. I'm a nuke submariner, but I'm not a. I haven't got the FTL figured out yet. That's the back end guys. That's what we used to say. We fight the ship, they push, right? And
okay.
so get a guy that pushes an FTL spacecraft around, and I'll interview him.
Yeah. Thanks. Thank you very much. Thank you very much. Appreciated. One of the great things about radio astronomy is the vast range of stuff that people get their heads around. I have great pleasure in introducing Pablo for something completely different. So